Hello everyone. Welcome to another lecture in calculus. Today we're going to be talking about the definite integral. We've been talking about the integral, sometimes called the indefinite integral, which is the same thing as an antiderivative. So what we refer to as an integral is an antiderivative. Here we're going to talk about a definite integral. And sorry, but I think you're going to have to wait until Cal 2 to find out really what this is all about. But we're going to talk about how to evaluate a definite integral. The definite integral of f of x from x equal a to x equal b, denoted this way, is evaluated as follows. And here's how we evaluate it. And before I go any further, note the difference in appearance between a definite integral and the integrals that we've been working with. The difference in appearance is this, which we'll call the lower limit. And that has nothing to do with limits that we talked about earlier. And this thing, which we will call the upper limit. In just a regular integral or antiderivative, we don't see an upper limit, we don't see a lower limit. So appearance-wise, this is what distinguishes a definite integral from an indefinite integral or antiderivative. And we can evaluate the definite integral numerically this way. Take capital F of x, where capital F of x can be any antiderivative of little f of x. Capital F of x is any antiderivative of little f of x. And the way we compute the definite integral of little f of x, we take the upper limit and plug it into the antiderivative, and then we take the lower limit and plug it into the antiderivative. And we subtract one from another. That's how we compute a definite integral. So before we talk about the significance of a definite integral, we're going to do, no, I'll tell you what. Yeah, we're going to do some exercises just computing a definite integral. And then we'll get to the significance of what a definite integral can represent. Might as well start off with something fairly easy. We have a definite integral. The lower limit is x equal 1. The upper limit is x equal 2. And this is our little f of x. Now, according to what we just saw, the way we evaluate a definite integral is that we find an antiderivative, any antiderivative of this function, and we plug in the upper limit, we plug in the lower limit, and we subtract. So let's do that. First of all, we need to find an antiderivative of this function. And remember, we were told any antiderivative will work. When we're computing a definite integral, any antiderivative will work. So why not just make things as simple as possible and choose the antiderivative that doesn't have a constant term? The antiderivative of 3x squared, let's say, that's going to be 3 times, add 1 to the exponent, divide by the new exponent, And we evaluate from x equal 1 to x equal 2. And the reason I didn't add a plus c here, I could have if I had wanted to, and that wouldn't have hurt anything. But the reason I didn't add a plus c here is because any antiderivative will work. So why not just simplify and use the antiderivative that has a constant term of 0? So the plus c goes away. Plus c is 0. Okay, so we have x cubed and then we're told we plug in the upper limit and we plug in the lower limit. So we have the antiderivative, capital F of x, evaluated at the upper limit, evaluated at the lower limit, and we subtract. So we get 8 minus 1 equals 7. And voila, we are done. Well, that was pretty easy, wasn't it? I guess we need to do another one. Okay, here's another definite integral. And the lower limit is x equal 1. The upper limit is x equal 3. And 2x plus 1 is our little f of x. So in evaluating this definite integral, the first thing we have to do is find an antiderivative of little f of x. Any antiderivative. Okay, antiderivative of 2x is 2x squared over 2. The antiderivative of 1 is 1x. Whoops, x equals 3. And then what do we do? By the way, note again that we chose the antiderivative that had a constant term of 0, because any antiderivative will do when we're computing a definite integral. So we have our antiderivative, and now what? We plug in the upper limit to the antiderivative. Well, you know what? Let me simplify this first. So I'm going to get x squared plus x so this is still my capital F of x. And now what do? We're supposed to plug the upper limit into the antiderivative. And then subtract the lower limit into the antiderivative. -1, okay. So plug the upper limit in first, plug the lower limit in second, and subtract. So we get 9 plus 3 minus 1 plus -1. So I guess it is just going to be 12. Let's do another example. Let's see, can we see that? Yeah, I guess we can. So x equals 0 is our lower limit, x equal pi over 2 is our upper limit, and cosine of x is our little f of x. So what's our first order of business? Get that antiderivative, right? Get capital F of x. And the antiderivative of cosine is, be careful now, the antiderivative of cosine is sine of x. Remember, the antiderivative is the function that we have to compute the derivative of to get cosine of x. Derivative of sine of x is cosine of x. So sine of x is the antiderivative of cosine of x. And then what? Plug in the limits of integration. Which one do we plug in first? It's the upper limit first, isn't it? So we plug in sine pi over 2 to sine of x. So we have the antiderivative capital F evaluated at pi over 2. The antiderivative capital F evaluated at 0. And by the way, let me point out again, since this is a definite integral, we didn't need to have a plus c here because any antiderivative will work, including the antiderivative that has a constant term of 0. So we chose the antiderivative that had a constant term of 0 just to make things easier on ourselves. Okay. Sine of pi over 2 is 1. Sine of 0 is 0. And there we are. Now we'll talk a little bit about the geometric significance of the definite integral. Here's a fundamental fact about definite integrals and something that we use in statistics among other areas. If f of x is non-negative, greater than or equal to 0, so let's see, how do we know if f of x is non-negative, greater than or equal to 0? Well, the graph of f of x lies above the x-axis. We'll allow the graph of f of x to touch the x-axis, but it won't dip down below. So the graph of f of x lies on or above the x-axis. So if f of x is greater than or equal to 0, the graph lies above the x-axis. The area bounded by the graph of f of x and the x-axis over the interval from x equal a to x equal b is given by the definite integral of f of x from x equal a to x equal b. And notice that x equal a and x equal b are the endpoints of this interval. Now, this is a lot to take in, and what we really need is a picture. And I'm going to give that picture, but I'm going to draw attention to a few things first. Things that we've stipulated. In this case, we've stipulated that f of x is non-negative. The graph lies on or above the x-axis. And in this interval, notice that a has to be less than b because a is the left endpoint. So we're assuming that a is less than or equal to b. And under those conditions, the definite integral gives us the bounded area. I'm going to leave this on the board for a couple of seconds, and then I'm going to draw a picture that depicts what this theorem is saying. Okay, let's start here, and bit by bit we'll sort of create what the theorem that we just looked at states. Here we have the graph of y equals f of x, and notice that since the graph lies above the x-axis, f of x is greater than or equal to 0. And notice also on the x-axis, a is to the left of b. So a is less than or equal to b. Now our theorem talked about bounded area between the graph of f of x and the x-axis over the interval from x equal a to x equal b. Well, here's the bounded area right here between x equal a and x equal b, or another way to say that is over the interval from A to B. This is the area that's bounded between the graph of f of x and the x-axis. And our theorem says, as long as f of x is non-negative and a is less than b, that this bounded area is equal to the integral, the definite integral, of x equal a to x equal b of f of x dx. You know what? Let me erase this. And write it this way. The area between the graph of f of x and the x-axis over the interval from a to b on the x-axis is the definite integral of f of x from x equal a to x equal b. So this area is equal to the definite integral of f of x, which is kind of an interesting fact because there are very few figures in geometry that we know the area of that are not completely bounded by line segments. We know the areas of triangles, rectangles, squares, parallelograms, rhombuses, pentagons, and so forth. But all of these are bounded by line segments. And we know the area of a circle, pi r squared, but the circle seems to be that lone exception, something that isn't bounded by line segments. We know the area of a circle, but most of the regions whose areas we know from geometry are regions that are bounded by line segments. So here's a region that's not completely bound by line segments, but we're able to compute its area. And we're going to see in Cal 2 that we can take regions that don't have any boundaries that are line segments, and we're able to compute them with integrals. So this is kind of an interesting thing that we can do. This doesn't have to be a region that's bounded by line segments, but we can compute the area using a definite integral. And I do want to add something to what I said before. And since I can't rewind the video, I guess I'm going to have to do it this way. For the moment, we're going to require that f of x be a continuous function. Earlier, we didn't stipulate that f of x had to be a continuous function, but we are doing that. We're going to say that f of x has to be a continuous function, and a is less than b, and f of x is non-negative. The one thing that I forgot, shame on me, but it's kind of important, is to note that f of x has to be a continuous function for this to work. So let's apply what we just learned. Here's a nice exercise. Compute the area bounded by the graph of f of x equals x squared plus 1 and the x-axis over the interval from 0 to 3 on the x-axis. Well, f of x is a polynomial, so it's continuous. So I'm pretty much assured that the area is going to be the definite integral of f of x from x equals 0 to x equals 3, provided I know that this graph lies above the x-axis. I'm not sure I know that yet, so I guess the first thing I have to do, and maybe the first thing I should do in any area problem, is just graph the region or graph the function. Okay, f of x equals x squared plus 1. You know what? We can do this using calculus because we spent some time just a week ago doing maximums and minimums and so forth. And with complicated functions especially, if we need to know if they lie above the x-axis or not, find the relative maximums, relative minimums, graph that thing, and then we'll know for sure what the function looks like and whether it lies above the x-axis or not. Here, this is kind of a simple function, so I'll show you something else. We all know what the graph of y equals x squared looks like, right? It goes through the point 0, 0 on the origin, and it's a parabola that opens upward. Now, what about y equals x squared plus 1, which is our function? To get this graph, I'm going to have to add 1 to both sides here, which means that I'm adding 1 to y. So graphically, I'm adding 1 to the y coordinate of every point on this graph. So if I increase the y coordinate of every point on this graph by 1, I'm actually sliding this graph upward by 1 unit. So here's the origin, and here's the new vertex. We've taken this graph, we've slid it up 1 unit. Does this graph lie above the x-axis? It sure does. Okay. So now let me draw a little bit of a prettier picture now that I know what my function looks like. Here's 0, 1, and here's the graph of the function f of x equals x squared plus 1. And we want the area between x equals 0 on the x-axis and x equals 3 on the x-axis. Forgive my writing. Okay. So we want this region here. The graph of f of x lies above the x-axis. So the area is going to be, let me erase some of this. I'm running out of room. And my f of x is x squared plus 1. Okay. So now all I have to do is compute the definite integral. So the antiderivative of x squared, what do? Add 1 to the exponent, divide by the new exponent, antiderivative of 1 is 1x. And we have our antiderivative, capital F of x. Okay. Plug in the upper limit. Plug in the lower limit. And we get 27 over 3 is 9 plus 3 is 12. Well, that's interesting. Another area of 12. And let's do another one. Another area problem. The area bounded by the graph of f of x equals x squared plus 1 and the x-axis over the interval from 1 to 4 on the x-axis. Okay, so how should we start this? We have to make sure that this graph lies above the x-axis, right? So let's graph f of x equals x squared minus 1. And again, I start with a function I know something about. Y equals x squared. We know what that graph looks like. It has a vertex at the origin. The rest of the graph is completely above the x-axis. Now I want x squared minus 1. So let's look at y equals x squared minus 1. And how do I get this function from this function? I take both sides of this function and I subtract 1. So my y here is y minus 1 over here. I'm taking the y coordinate of every point on this graph and I'm subtracting 1 from it. So this is what the graph of y equals x minus 1 looks like. And part of that graph goes below the x-axis. But let's investigate something. Where is it that this graph actually crosses the x-axis? Well, in other words, where is y equals 0? Y is equal to 0 and x squared is equal to 1. So that means that x could be positive 1 or x could be negative 1. Those are the x-intercepts. So maybe all is not lost because we're being asked to find the area bounded between the graph of f of x equals x squared minus 1 and the x-axis over the interval from 1 to 4 on the x-axis. Let's take a look and see what that looks like. I'm going to exaggerate this a bit. 2, 3, 4. The graph of f of x equals x squared minus 1 over the interval from 1 to 4 on the x-axis. This graph lies above the x-axis between x equal 1 and x equal 4. So I guess it doesn't really matter what the function does over here, does it? Over here to the left of x equal 1, it doesn't matter that the graph goes below the x-axis. All we really care about is, what is this function doing between x equal 1 and x equal 4? Well, it lies above the x-axis. So I guess we're good to go. Over the interval that we're working with, from x equal 1 to x equal 4, f of x is non-negative. The graph lies above the x-axis. So, no problem. No problem. First thing we do, compute the antiderivative. So add 1 to the exponent, divide by the new exponent. 1 is a constant. The antiderivative of 1 is 1 times x. Okay, now we evaluate the antiderivative at the upper and lower limits. Upper limit first, right? So we're going to have x cubed evaluated at 4 and x evaluated at 4. So this is our antiderivative, capital F, evaluated at 4. And from that we subtract the antiderivative evaluated at x equal 1. So take 1, plug it into x, 1 cubed over 3. Take 1, plug it in for x, 1. And what do we have? 4 cubed, my goodness, 64. 64 thirds minus 4 minus 1/3 minus 1 64/3 minus 1/3 is 63/3, which is 21. And negative 4 plus 1 is negative 3. So essentially we have 21 minus 3 is 18. You know, that was a close call. The graph of f of x dipped below the x-axis, but thank goodness it wasn't in the area over which we were trying to compute the bounded area of the region. But what would we have done if that would have been the case? Ooh. What if the graph had gone below the x-axis in the region whose area we were trying to compute? Okay, suppose the graph of f of x is below the x-axis. F of x is continuous, but f of x is negative. The graph of f of x lies below the x-axis. Then the area bounded by the graph of f of x and the x-axis over or under the interval AB on the x-axis is given by area equals the negative of the integral from x equal a to x equal b of little f of x. And again, I'm going to let you look at this for a few seconds. I'm going to erase it, and then I'm going to draw a picture of what this is telling us. Here's the graph of a function y equals f of x, where f of x is negative. The graph of f of x lies below the x-axis. And we want to compute the area bounded by the graph of f of x and the x-axis between x equal a and x equal b. In other words, we want to compute this area. And that area is given by the negative of the interval from x equal a to x equal b of little f of x dx. So if the graph lies below the x-axis, the way that we compute this area is we compute the negative of the integral of f of x from a to b. Now let's see if we can apply this to a nice example. It really is a nice example. Okay, this is a nice exercise. Find the area bounded by the graph of f of x equals sine x in the x-axis over the interval from 0 to 2 pi. Okay, so let's have at it. Now sine of x, that's our little f of x. And we have to compute the antiderivative of sine of x. That's negative cosine of x. So here's our capital F of x. From x equals 0 to x equals 2 pi. Okay. So we plug in the upper limit. And here's capital F evaluated at 2 pi. And we plug in the lower limit. Capital F evaluated at 0. What's cosine evaluated at 2 pi? Let's see, it's 1, isn't it? Okay. So this should be negative 1 minus negative cosine of 0. What's cosine of 0? That's 1, isn't it? So we have negative 1 minus a negative 1 is 0. Well, I'm horribly frustrated. For some reason or other, I'm pretty sure that this can't be the entire bounded area from x equals 0 to x equal pi over 2. There's got to be more than 0 area bounded there. And yet, according to what I did, it says the area is 0. Yeah, all that work for nothing, right? Wait a minute, wait a minute. Why didn't you people stop me? None of you said anything. Anytime we do an area problem, we're supposed to do what first? Graph the function, right? Or graph the region. I didn't do that here. Did any of you try to stop me? I didn't hear anybody say anything. You know what? I guess this is the kind of thing that happens when we don't follow the rules. Whenever we do an area problem, we want to draw a picture of the region, graph the functions. Otherwise, we may end up having mud on our face like I did here. So let me try to do this again, and let me do it following all the steps and all of the rules, and maybe this time I can get it right. Okay, let's do it the right way. We won't cut corners, we won't skip any steps, because we want to make sure we get this right. And getting it right is more important than getting it done quickly, or at least it should be. So we got to graph the function. Well, that's not a problem. We know what the graph of sine of x looks like. So at x equals 0, sine of x is 0. So this is a point on the graph. And at pi over 2, sine of x is 1. At x equal pi, sine of x is 0 again. And at negative 3 pi over 2, sine of x is negative 1. And then at x equal 2 pi, sine of x is 0 again. Okay, well, here's our problem. The graph of sine of x from x equals 0 to x equal pi over 2 does not lie completely above the x-axis. As a matter of fact, half of it lies above the x-axis, half of it lies below the x-axis. So I got to do each of these areas separately. Now, there is a shortcut that we can use doing symmetry, but I don't want to do that right now. In general, if we're doing an area problem and the function goes above the x-axis and below the x-axis and so forth, we're going to have to break the problem up into separate integrals. So I'll sort of write out in words what my intention is. From x equals 0 to x equal pi, the graph lies above the x-axis. So we can compute that area in one fell swoop. And from x equal pi to x equal 2 pi, the graph lies below the x-axis. So we can compute this area in one shot. Whoops, 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 whoops. So we're going to compute this area. And we're going to compute this area. And we're going to compute those areas separately. Now, by and large, in this kind of an exercise, that's what we have to do. Which means we're going to have two separate integrals. So we have the integral from x equals 0 to x equal pi. And our function is sine of x. And this looks exactly like it should, because from x equal to 0 to x equal pi, the graph lies above the x-axis. Now we're going to add to that the area between x equal pi and x equal pi over 2. And here the graph lies below the x-axis. So we're going to have to compute the negative of that integral from x equal pi, x equal 2 pi of sine of x. That's how we're going to have to do it. Two separate integrals. And I'm going to keep the graph because there's something interesting about our answer. It's not something we need to know, but it's just something interesting. So let's see. Compute the antiderivative, negative cosine of x. From x equals 0 to x equals pi. And this is our capital F of x. And then we're adding the next thing, which is negative the integral of sine of x. So we're going to have negative the antiderivative, negative cosine of x, from x equal pi to x equal 2 pi. And if I just do away with the minus signs, I have negative cosine of x. And I'll tell you what, I'll plug in the limits here. Negative cosine of x minus, you know what, maybe I should have quit while I was ahead. Plug in the upper limit, x equal pi. So negative cosine of pi minus the negative of cosine evaluated at the lower limit. And we have negative and negative here, so that's just positive. Cosine evaluated at 2 pi, upper limit, minus the antiderivative evaluated at pi. So this is negative a negative 1 minus a negative 1. This is 1 minus a negative 1. So we have 1 plus 1 is 2, plus 3, plus 1. Plus 1 is 3, plus 1 is 4. That's our area, 4. And this is something that I would not have expected. If I were doing this exercise for the first time and I was computing the area bounded between the graph of sine of x and the x-axis, I would expect the numerical value of the area to have pi in it somewhere. It doesn't. The area of these two regions combined is just 4 square units. The area is a whole number. It's not a function of pi, just 4 units, which is a pretty amazing thing, really. The area bounded by the graph of sine of x and the x-axis from 0 to 2 pi, 4 units, a whole number. That really is something incredible. Now, as far as definite integrals go, there's one more thing that I haven't told you that I need to tell you, and this is kind of a biggie. It has to do with computing a definite integral where we also have to do U-substitution. And there's a booby trap there. And the best way to illustrate where the booby trap is and to how to deal with that booby trap is just to work through an exercise. So that's what we're going to do. Definite integrals and U-substitution. There are booby traps here, or maybe just one booby trap, really. But we need to see what it is, and we also need to devise a method of doing this U-substitution such that we won't miss the booby trap. So I guess the first thing we do here is we determine whether U-substitution is appropriate. And yes, we're still riding our bicycle with training wheels. We won't always write these 5 steps down, but for the time being, we want to do these 5 steps and write them out so that they are ingrained in our memory permanently. This is something that we really do want to get right, and we want to continue to do it right forever and ever. And U-substitution, hey, it's all through Calculus 2. If we get this down pat now, Calculus 2 will be very manageable for us. If we don't get this down pat right now, we are going to get squashed like a grape in Cal 2. So let's keep the training wheels on, swallow our pride, and learn how to ride our bicycle well before we take the training wheels off. Is U-substitution appropriate? The first thing we look for is a composite function. And I say yes because we have a function raised to a power. And a function raised to a power is always a composite function. So the raising of something to the 3rd power is the outer function, and x squared plus 1 is the inner function. Now, do you remember the criteria or the rule of thumb? The rule of thumb that we used to select U in criterion A? We let U be the inner function, right? So let U equal the inner. So U equals x squared plus 1. Now, what about the second criterion, B? We're looking for, well, not necessarily an exact function derivative pair. If we have an exact function derivative pair, that's fine. But if we don't, an approximate function derivative pair will work. And is there an approximate function derivative pair? And I guess we have our choice here. There definitely is. We could either say x squared and x, where x is the function and x is the derivative. Or we can say x squared plus 1 and x, where x squared plus 1 is the function and x is the derivative. And what's our rule of thumb here? We let the function of the function derivative pair be U. So let U equal the function of the function derivative pair. So we're going to have U equals x squared, or we're going to have U equals x squared plus 1, depending on which one of these things is really our function derivative pair or our approximate function derivative pair. And I guess in each case it's approximate, right? The derivative of x squared is 2x, so it's just a constant multiple off from x. The derivative of x squared plus 1 is 2x, so it's only a constant multiple off from x. Well, we won't worry about which one to pick right now. We'll go to criterion C. And remember what that is? Do both criterion A and criterion B recommend the same choice of U? And we want to answer yes to this, which means that criterion A and criterion B have to give us the same choice of U. Criterion A says U should be x squared plus 1. So this is the one that we're going to go with in criterion B. So if we have a choice of function derivative pairs, we're going to choose the function derivative pair whose function is also the inner function of the composite. Or said differently, we're going to choose the function derivative pair that recommends the same choice of U that criterion A recommends. So there were two function derivative pairs, but for the sake of our analysis, this is going to be the function derivative pair that we work with. And we answer yes to all three questions. So that means that U sub is definitely appropriate. Now, in addition to determining that U substitution is appropriate, step 1 also tells us what U is going to be. So step 2, we compute du, and we write down what U is. U is x squared plus 1, and that means that du dx is 2x, and that du is equal to 2x dx. And since we only have an approximate function derivative pair, I'm going to leave a line blank here. And you know what? Since we're working with a definite integral, it's going to turn out that in addition to this one blank line, I'm going to need a couple more blank lines. So I'm going to leave about 3 blank spaces here. I'm going to need them. And my step 3, analyze in terms of U and du. And I think my integral was x equals 0 to x equal 2. And there was not a u in there, I'm sure of that. X squared plus 1 cubed times x dx. And let me just make sure that's what it was. My memory is not what it used to be. X goes from 0 to 2. X squared plus 1 quantity cubed times x dx. Okay, this is it. And we analyze this integral in terms of u and du. u is x squared plus 1. And here we have x squared plus 1 cubed. So this is u cubed. X dx, I don't see x dx anywhere. But I see something like x dx. I see 2x dx here. Now, what do I have to do to both sides of this equation to make the right-hand side look like x dx? If I divide both sides by 2 or equivalently multiply both sides by a half, this side will be x dx, won't it? So that's what I'm going to do. I'll multiply both sides by a half, and I get x dx. So in terms of u and or du, this thing, x dx, is 1/2 du. Okay, excellent, excellent, excellent. So I rewrite this in terms of u and du. Now here's where I'm about to step on a booby trap. There's a landmine here and I'm about to step on it. Do you see what it is? Step 3 is analyze our integral in terms of u and du. And I haven't done that completely. My limits are still in terms of x. And by the way, if you look in the book with the integrals, they don't have x equal 2 and x equals 0. They just have 2 and 0. Deliberately, I put x equals 0 and x equal 2 here, so I'm aware of the variable in terms of which the upper and lower limits are given, exactly because of a situation like this. I'm looking at these limits and I'm saying, this is not in terms of u. This is not in terms of u. Wrong, wrong, wrong. I'm about to step on a landmine and I don't want to do that. I want my limits to be in terms of u. Everything should be in terms of u. So, you know these extra 2 lines that we left blank here? I left them blank just so that I could determine what the upper and lower limits are in terms of u. Now, what about x equals 0? I'll write it out here. When x equals 0, u equals, well, what does u equal? U is x squared plus 1. So when x is 0, u is x squared plus 1, which is 0 squared plus 1, or just 1. And now, okay, I'll put that down. When x is 0, u is 1. Now, what about when x equals 2? I'm going to write it out. When x equals 2, u is x squared plus 1. So x is 2, so this is 2 squared is 4 plus 1 is 5. So now my upper limit is 5. I avoided the landmine. Now, some people may ask, couldn't we have just done the entire integral, the antiderivative in terms of x, rewritten the answer in terms of x, and then plugged in the limits? In other words, couldn't we have just done the indefinite integral, the antiderivative, and rewritten it in terms of x, and then plugged these limits in? And the answer is yes. I recommend against doing that because it seems like people forget over time that if they don't rewrite the limits in terms of u, they can't just plug the limits in terms of x in for u. People who don't do it my way, over time it seems like eventually they forget that when they integrate, these limits, if they're in terms of x, can't be plugged in for u. So I like to do it my way because if we're conscious to do it my way, there's no way that we can goof up. Now let me rewrite this, and I'm just going to bring the constant out front. Then we come to step 4, integrate in terms plural of u. So we have 1/2 the integral from u equals 1 to u equals 5 of u cubed du. So that's 1/2, add 1 to the exponent, u to the 4th, divide by the new exponent, 4, and we plug in the upper limit. And we plug in the lower limit. And everything is over 8. So 5 to the 4th, let's see, 5 squared is 25, so this is 25 squared. 625 over 8 minus 1 over 8. So that's, hey, excuse me. I'm sorry, where were we? 625 minus 1 is 624 over 8. And 24 is divisible by 8, and 600 is too. Okay. Let's see. 8 goes into 62 7 times. 8 goes into 64 8 times. Wow. Okay. So our integral from x equals 2, from x equal 0 to x equal 2 of x squared plus 1 x dx is 78. And notice something. This was a U-substitution exercise, but it was also a definite integral. And we didn't have to do step 5. We didn't have to rewrite the integral in terms of the original variable, or we didn't have to rewrite the answer in terms of the original variable, because the answer just turned out to be a number. So technically, in step 4, when we got to this point and we got our number, we were done. With a definite integral, there was no need to rewrite everything in terms of the original variable because our result is a number, not an expression in terms of variable x or variable u. So from now on, when we do U-substitution and we do definite integrals, in step 3, when we analyze in terms of U, we are going to rewrite these limits in terms of U and prevent ourselves from making an unnecessary mistake.